Now I'm choosing here the weight Wm, the memory weight. And the reason is that this is the guy who needs backpropagation through time, right? So as you remember last time, the output layer, this guy, the red weight, this one is actually very simple to compute the gradient with respect with, right? Because it does not really go deep in time, right? But the yellow one is actually connected through time, so I want to just focus on that one. So say I want to compute the gradient with respect to weight Wm. How can I do it? Well, what do? Gradient of the loss with respect to the weight, right? So this Wm is connected to, I mean, first of all, we do know the gradients up to the outputs, right? Correct? So I do know the gradient of loss with respect to the first y and last y, everything, right? That I know. Second thing, Wm shows up in what variables here? Does Wm show up in y1? Doesn't that? Not directly, but it shows up somewhere there, right? It's going to impact. If you think like a computation graph, it's impacting that guy, right? Is it impacting y2? Yes. y3? Yes. yt? Yes. Everybody, right? So this means that if I want to do that, I would say, okay, the gradient of loss with respect to Wm is going to be the gradient of y1, loss with respect to y1, times gradient of y1 with respect to Wm. Should I stop here? What should I write next? y2, y3, and so on till yt, right? Every single of them is a function of Wm. So chain rule going to apply to all of them, right? So I'm going to have the complete chain rule here. And it's not anymore simply decomposing, right? Because Wm is somehow contributing to every single of them. So I basically need to compute every single of them. So I told you that I have these gradients. The main thing that remains, so I want to compute the summation, but the main thing that remains for me to compute is this second gradient, right? Because the first gradient is something that I can simply compute, right? So that is not a problem. So basically, I only need to compute the gradient of every single output with respect to the memory weight, right? Well, so let's go ahead with this guy. Now, yeah, I have this explanation here just for those of you who might be a bit obsessed with, like, what does this gradient mean? I guess, like, by now, everybody has somehow gave up this kind of question. But this notation here is a kind of, tensor-like gradient, right? So you have yt, that yt could be a vector, right? And you should compute the gradient of every single entry inside that vector with respect to the whole matrix, right? Wm. And this is a giant tensor, but you don't care, right? This is at the end one array of gradients, right? Okay. Now, yeah, oh, I spoiled everything. So now that I want to compute this guy, exactly like the thing we did in depth, or the thing that we did last time with Elman network, one thing that we can see is that this yt, of course, depends on Wm, not only through the depth that is connected in time t, but also through the time connections, right? And it's going to make the whole story a bit complicated. But we could do, we could use simple gradient notation, but I'm going to keep things easy as we did it last time in chapter 5. So I'm going to go with a very single case where we are computing one single output and we have one single weight. So all the gradients going to be derivative. It's going to make it easier for you to write it down, right? Just to make the visualization simple for you. Everything going to just extend when you replace that derivative with the gradient notation. Everything could be the same thing. So when we have a very dummy RNN with single dimension input, single dimension hidden state, single dimension output, then this is going to be the case, right? So your input goes in, it's going to get multiplied with one weight. This is on its own weight W1. Your memory gets multiplied with Wm, and your hidden state is computed, then the hidden state is going to give you the output, right? And everybody in this neural network is simply in scalar, so you can simply compute the gradients by taking derivatives, right? So you start with the first input, one weight, hidden state, one weight, computes the first output, and so on. You go towards the end. And the things that you are now required to compute is the derivative of every single time instant output with respect to the memory weight. So how can we do it? Let's start with these stuff, like the things that we have at time t. At time t, the output is given in this form, right, in terms of the hidden state. Now, if I want to compute that derivative, what should I do? I am trying to compute the derivative of y, which is this guy, with respect to my weight, Wm. How can I do that? Where is Wm hidden? In HT, right? So I'm going to write down the chain rule, right? I'm going to say the gradient with respect to Wm is basically the derivative of my y with respect to the hidden state times hidden derivative with respect to the memory weight, right? Great. So I can simply write it down. So this derivative is very simple because you have this guy. Well, it's going to be just a weight times derivative of the activation. So I'm going to keep it here. And then I have this derivative, right? Derivative of h with respect to the weight, right? Now, where does this derivative show up? So I have this ht here, right? And this guy is actually depending on input xt in this form. And it also depends on wm and also depends on ht minus 1. Now, I think we did it last time. I guess you have a clear idea how we should take this derivative. How should we do it? What are the components that show up in the chain rule when I want to take the derivative with respect to Wm? Is ht a direct function of Wm? Is it or not? Once again, is ht a direct function of Wm? Does Wm show up in computation of ht directly? Yes or no? Look at the board. What is ht? Look at that line. What is ht? So it is a direct function of Wm, right? So I can take the direct derivative with respect to Wm, treating everybody else as a constant, right? This is one term. Is there any other term that I should take care of? Is there any other guy inside that expression who is a function of Wm as well? ht minus 1. ht minus 1 is depending on Wm as well, right? So if you want to just do that, you might say that, okay, ht is a direct function of Wm. It's also a function of ht minus 1, and both of them depend on Wm. So how you compute this derivative of ht with respect to Wm? You would say, okay, I first compute the derivative of this direct function, so derivative of this g with respect to Wm times derivative of Wm with respect to Wm, which is 1, right? There's nothing here, 1, right? The next term that I'm going to include, what is it? It's going to be the derivative with respect to ht minus 1 times the derivative of ht minus 1 with respect to Wm, right? Cool, right? So I have this guy. I can simply write it down in this form. So this is derivative of g, this guy, and g is basically this expression here with respect to Wm. It means that you look at this ht equal by that. You just treat everybody as a constant. Only Wm is the variable, right? And you take the derivative, right? And then for the second one, you get you treat everybody else as a constant. ht minus 1 is a variable, and you take the derivative, right? So that's it. Okay. Cool. So yeah, here is just a bit of extra explanation. So I think everybody's seeing it. Sometimes when I'm a bit in rush, so people don't see it, then I just keep it like this, so makes it easier, but you already can see it. So yeah, if you want to take the derivative of that guy with respect to Wm directly, so derivative of g with respect to Wm, it's simply ht minus 1 times derivative of the activation, right? So when we have I think you remember from chapter 5, when we have such expressions, every derivative that we take is always derivative of an activation times one of the variables, right? And if you are taking with respect to hidden variables, the features, it's going to be one weight that is getting multiplied. If you are taking the derivative with respect to weight, it's going to be the corresponding feature, right? So here when I take the derivative with respect to Wm, so ht minus 1 is going to show up times derivative of the activation. When I take the derivative with respect to ht minus 1, what's going to be the factor that shows up? Wm, and then this is again derivative of the activation, right? So I can write it down in this form. So derivative of g with respect to Wm is ht minus 1 times derivative of activation, and derivative with respect to the previous hidden state is Wm times derivative of the activation. Yes? Yes.
For the last term, the derivative of ht minus 1 with respect to Wm.
Right.
Is it also related to ht minus 2?
Yes, we are going to do that. Yeah, no worries. Yeah. So we haven't computed this yet, right? We just computed the other guys. Okay, so that is going to conclude the derivative of ht with respect to Wm in this form. Now, this is the thing that I want you to see, and I mean, the details are not that important. So this guy is a derivative of the activation. It should be here, right? Because you are taking derivative with respect to the expression inside the activation, right? So the derivative of activation always show up. Now, the term that you have, if you didn't have the time connection, this guy going to disappear, right? And then you have a classic one. Derivative of activation times feature, right? Now you have that guy, activation plus one derivative in time, right? One back in time, right? Everybody's cool, right? Okay. Now, here when you look at this guy, you do know everybody here because you do know zt. Zt is basically that expression, the one which you computed before activation in your hidden layer. That one you have. You can just simply plug it in here. This guy is something you computed in your in your forward propagation. You already have it. You can compute this one. But this guy, we don't have it yet, right? Derivative of ht minus 1 with respect to the memory weight, we don't know it, right? What we can do, we just go backward in time, right? We just keep on doing the chain rule till we are finished, right? So the thing that we're going to say, okay, I want to compute this gradient, the gradient of ht minus 1 with respect to Wm. How can I do it? Basically, I do the same thing, right? I'm going to write down ht minus 1. So I say ht minus 1 is written in terms of ht minus 2 and xt minus 1 in this form, right? Now, what are the terms that are going to show up in my derivative? Look at ht minus 1. Is it a direct function of Wm? Yes. Wm shows up in its computation. Is there any other variable in this expression which is depending on Wm? ht minus 2, right? So I need to take care of both of them. So I'm going to write it down in this form, right? So I'm going to write down, so it's going to be derivative with respect to Wm plus the derivative with respect to ht minus 2 times derivative of ht minus 2 with respect to Wm. Now, this is exactly the same problem as you had before, right? This is the same thing we did at time t, but now we're doing it at time t minus 1, right? So look at this guy. This is zt minus 1. Your ht minus 1 is an activated version of it. And here you have the same thing. ht is an activated version of zt, and zt is exactly the same expression, only shifted in time, right? So you're going to end up exactly with the same expression here as well. So your derivative at time t minus 1 is going to be your activation derivative at time t minus 1 times your previous hidden state plus derivative of your previous hidden state, right? And if you keep on going in time, you always see the same expression, right? Everybody's clear? So if you go for time t minus 2, then you're going to have same expression shifted in time by 1, right? So it's going to be derivative at t minus 2 times ht minus 3 plus weight times derivative of ht minus 3, right? And so on, you're going to keep on going at time, right? So one thing that you can say that, well, I'm writing down my derivative of the output with respect to weight. By backpropagation, I just go to my hidden state. And then when I get to the hidden state really needs to go back in time, right? So I need to just compute from time t. I just go backward in time, right? At time t, I need to know what is this derivative. So I compute it in terms of the hidden state of the previous time and its derivative, right? But then how I can find its derivative at time t minus 1? Well, again, I use the same formula, but I change t to t minus 1, right? Everybody's clear? Questions? So this is like you start from the output. You just get to the hidden state at your time, right? And then you have this recursion, right? You say my derivative at time t depends on my derivative at t minus 1, right? And that guy depends on the derivative at t minus 2, right? And all of them show up exactly the same expression. And there is no magic here because you actually use exactly the same neural network to compute them, right? It's only time that has changed, right? Everybody's clear? Questions? Now, this guy that you see, you can actually simply compute it by recursion, right? You start at time t, you do t minus 1, t minus 2, and so on, right? And then you end up to the point that you end up with time 1, right? When you get to time 1, then you would say, okay, the derivative of h1 is going to be h0 plus derivative of h0, and derivative of h0 is simply 0 because h0 was your initial state, right? And you just initiated it. It was not a function of Wm, right? And that's over. So you start at time t, you just go back all the way to time 0, and you stop, right? And every time you exactly do the same updates, right? This is what we call it backpropagation through time. Same formula as before, you only now backpropagate in depth first and then through time, right? So it's like you get at time t to this ht, and then you say, okay, this derivative, how I can compute it? Well, based on the derivative of ht minus 1. What about that? ht minus 2. And what about that? You go on till you get to h1. What is the derivative of this guy? Well, it depends on the derivative of h0, but that guy actually does not exist, right? That's 0. And I stop, right? Now, one thing that you see here, this is a shallow neural network, but if your sequence is very long, you're going very, very, very long in depth when you do backpropagation. That depth is the time depth, is not the network depth anymore, right? And this means that even the shallowest network you can think of, as long as it's processing quite long sequence, it's going to experience vanishing or exploding gradient, right? Questions? Well, so now what you do usually in time is that, as I told you, since the formulas are exactly the same, then one thing that you should keep in mind is that when you are backpropagating through time, you really don't need to do the whole backpropagation every single output, right? Because if I start by computing the gradient of at time 1, right, I just go 1 back in time and then I stop, right? When I go 2, then I need to get from h2 to h1, right? And then when I got at h1, then I already know the gradient of the previous ones, right? Because I already computed previous time, right? So every time that you progress, right, you are going to carry those gradients with you. So meaning that if you, for example, go all over the sequence in time, and you get to the last output, and you backpropagate all over through time, right? You do have all the gradients that you need, right? So any other gradients that you want to compute, you basically compute it immediately, right? So the guy who is going to impact is the last guy, right? That is the longest path you're going to have, correct? Just look at this guy. If I get to this one, right? If I do compute gradient very last hidden state, then I need to know the gradient of all previous guys, right? To be able to compute it, correct? Yes? The new one, right. You can think of it like this if you are going forward in time, right? But we usually like to go backwards, right? Because we need to wait, like all the outputs are there, and then we start to backpropagate, right? And the thing that we do is like we compute the complete output, then you backpropagate the last time, right? And then once you compute everybody, now if I want to compute at this time, I get to this guy. It's true that it's depending on everybody else, but those guys are already computed, right? So I can immediately use them, right? So that's the point. So if you want to just if you have already computed at time t, then you already have all the gradients at time t minus 1. So there is no need to again backpropagate through time. You basically can use it. So then efficiently, if you want to implement it, you backpropagate. You do the forward propagation from beginning of time to the last time, and then you backpropagate in the last time, and everything is over, right? You already have computed everything that you want, right? But one thing that is important here is that here you really have sequential processing, right? When you are computing the gradient, every time depends on the previous time, right? So you cannot immediately do parallel processing. It's a bit harder to do it. This is why transformers are more popular, because they somehow disconnect these time connections directly and then implement it through another process. We call it attention, right? And that one built parallel processing into the process. Okay, so this is backpropagation through time. So you start with your output, then you need to compute this gradient, and then you go back in time, right? In every time you compute the previous one, the gradient in terms of the gradient of the previous one, and you stop when you're at the very beginning of time, right? Now, as I told you, if you do that, you expect to see vanishing or exploding gradient, and this is a total valid expectation. So you could definitely see that, and this is something that people used to see for quite some time, okay? And as I said, like in the very basic ones, people started to see explosion more. And the reason was that like they wanted to somehow avoid vanishing by somehow making the network shallower and then making those features larger in amplitude. But then, as you can expect, like it's going to show a concentration behavior, right? It's either going to be 0 or going to infinity, right? And then just they didn't want to have 0, then it starts to go to infinity, right? And people thought like it's a very hard thing to do. Now, yeah, here I think you obviously see it already, but if you just want to expand it, you can see that like if you just go over time, then every time you're adding up all of those derivative of the previous features, right? And they are getting multiplied to each other every layer. So you're going to keep going like this, right? Right? Everybody's clear? So what is happening here? So one thing that I want here to just emphasize a bit is that it's true that you see vanishing gradient, but it's a bit different kind of circumstances as compared to the vanishing gradient in depth. And this guy was seen more, say, historically earlier than that one. So let's just look at this sequence. So let me just show it once again. So I am at time t, I compute the gradient, I end up with ht, right? ht minus 1. And now I want to compute the gradient of that one. So this is going to be the second term, right? So I have the gradient at time t minus 1, and then the gradient at time t minus 2, and so on. All of them are going to stack to each other, right? So the next term is the one which is taking into account ht minus 2, and you keep on going like this till you get to h0, right? Now, the gradient that you are going to compute at time t is going to look like this guy, and that guy is somehow having one coefficient times ht minus 1 plus another coefficient times ht minus 2 plus another coefficient times ht minus 3, and so on, right? Correct? Okay. That's cool. Now, you have this kind of coefficient, right? This is the coefficient that is going to get multiplied with that particular ht minus I, right? So I times steps before, right? And if you look at this guy, how many multiplicative expression it has? I multiplicative expressions, right? So it means that when you are at time t, your gradient is going to get impacted from your hidden state in the previous time, right? And the coefficient that is carrying the gradient for you is just one term, right? 2 time steps before, that hidden state is also bringing you some information. That makes sense, but the gradient component is multiplied with 2 activation derivatives, right? And if you go I time steps before, then you have I different terms multiplied to each other. This makes you one coefficient, and that coefficient multiplied with that hidden state is the information you are carrying, right? So this is the thing that is going to happen, right? And again, this term that you see here, this multiplicative term, when you go very deep in time, it can show vanishing or exploding behavior, right? But one question here is that if you look at this expression here and say the vanishing gradient behavior happens, okay? Do you expect your gradient to be 0? It's not 0, right? It is not 0. What's going to happen to the gradient then? The old time memory is not going to show up, right? Everybody's clear? So if the vanishing gradient happens, then it's not the problem that you get the gradient 0, because when the vanishing happens, say like vanishing has started to happen here, like this term is very small, right? Then these guys from ht minus I to h0, all of them are roughly 0, right? But you still have ht minus 1, ht minus 2, and so on, right? So vanishing gradient, when it happens in time, you basically, I mean, this is the same story as I told you before. I mean, it could explode, it could vanish, but when it happens, this simply means that the gradient that you are computing is not being impacted with the hidden state at very long time before, right? It's just going to get impacted with the hidden state in the recent time, right? Yes? Yes, that's the point, right? Well, yes, but since they are using transformers, I mean, that behavior is getting like extremely low pronounced, right? So at the end of the day, well, yes, any
Why, like, you know, sometimes you like start talking to like LLM or whatever, and then at one point, like, it forgets what you already told.
yes, yes.
It's a similar mechanism. Like,
Roughly, yes. But in the language model that you have nowadays, is like it's a transformer, and a transformer can process up to a specific number of tokens, right? So when you do that, this means that you have a giant input, and for that giant input, you don't lose any memory because you do attention. The problem that is happening is that, say you speak so much with the language model that you are just exceeding that token size, and then the language model needs to extract some context from your first, say, batch of conversation and carry it to the next batch, right? And as it carries out like this, gradually it starts to forget it. That's right, right? But again, you can do cross-attention to somehow carry more information. But eventually, if you think like theoretically, somewhere in the infinite time, you're losing some information from beginning of time. That's definitely the case. But this time window for nowadays language model is so large that practically we can think of it infinite. But with a very basic RNN, yes, that's very small. Exactly. So everybody's cool? Everybody gets the vanishing gradient behavior here? So the vanishing gradient behavior does not show up as you see 0 gradient. That is not going to happen with RNN. The thing that is going to happen is that you see the memory is being limited to the recent ones. So what does it mean? It means that if you go over a text, then at some point it starts to forget what the initial tokens were. What were the initial words, right? It's going to, at the end, somehow speak about the bunch of last words, right? And the reason is that you are not carrying information. Simply, the information about those guys is showing up in your memory by their gradient, and their gradient is just vanishing through time, right? So that is the problem that you see. So vanishing gradient through time is going to limit your memory, right? And then how you can resolve it, then people started to just come up with some remedies for that. First of all, you cannot really say that you can handle this issue. So theoretically, if you think about it, at the end of the day, any computation model is going to have a limited memory, right? This means that if you have a giant sequence, then it needs to just go over it batch by batch or part by part, and then gradually this behavior is going to happen. So you are not going to completely remove this property, this behavior. This is like overfitting, somehow exists in the sequence, right? And as a human being, as an intelligent creature, we also have the same thing, right? If something happened long time ago, unless it's like extremely important thing to us, we don't remember it, right? We somehow lose attention to that, we lose memory of that, even though having that could help us do better decisions, but, well, it's our mind, right? We don't have infinite capacity, right? Same thing with the neural networks, but we can nowadays efficiently get rid of them, get rid of this behavior, at least to the extent that it gets even better than us, right? This is why it's happening with the language models nowadays. Now, how we can resolve it, the thing that we can do, we can just come up with some simple remedies. That was what people used to do. But then the idea of gating was somehow similar to the skip connection in time. And then people see that if they do gating, it's going to do more efficient. And the idea of gating came over. Now, one thing that I want to indicate once again here. So I think I indicated enough. But the point here is that when you are actually seeing vanishing gradient through time, you just see the impact by losing memory, right? You just shorten the memory that you have, right? And when you want to get rid of that issue, it means that you want to extend your memory through time, right? Okay, so basic approaches that people started to do were, one of them was to just change the activation. So tanh activation. There are some old studies. If you can, I try to find one of them. I need to search again. But there are some very old studies where people put, for example, one deep in time, simple neural network with sigmoid, with, I mean, ReLU doesn't make too much sense, but say, for example, soft ReLU, and also with tanh. And they show that this concentration behavior is extremely less pronounced using tanh, right? And then they say, okay, maybe tanh is the best idea. So this was the reason that tanh became sort of convention for recurrent neural networks. And the other idea was to just do truncated backpropagation through time. And what does it mean? It means that you start with your sequence, you go somehow over time, and when you are here in the middle, you don't go all over your sequence. When you are here, you stop, right? So somehow you take this subpart of your sequence as a kind of one, say, sample, right? And then you update, right? When you update, you are just backpropagating through time over a short part of your sequence, right? And then you don't see the vanishing gradient behavior, right? So your weights are going to get updated with the information from time, say, 0 to the time that you are in, right? Then you are here, you have already updated your weights, right? You keep on going on the sequence by the updated weight, right? And then you go for another part of your sequence, and then you update, right? So now, second time that you update, you basically don't get the impact of the first part anymore that much, right? But the thing is that you somehow incorporated that impact in your first update, right? And you could hope that those weights that you end up at the very end are somehow carrying information of the first times, right? This was the idea of truncated backpropagation through time. Quite old idea. It's not worth anymore to just get it in details. But at some point of time, it was something that people teach and use in practice, right? But the most sophisticated version, which somehow resolved the issue essentially, was the gating approach. And this is what we are going to talk about next. So